part of what we've done today, we've already done before. The main thing that's new is going to look significantly newer to you. But for the most part, same kind of concepts. General solutions. We have found general solutions already. For example, if I gave you a function like 3x squared plus 2. Okay, 3x squared plus 2. And I asked you to integrate that thing. What would my antiderivative of 3x squared plus 2 be? A and H, what would my antiderivative be? Yep. Plus, what's the antiderivative to? 2x plus c. Good. Boom, that's it. He just found the general solution. He started with a function. We took the antiderivative. We didn't have any bounds. That's why he has a plus c on the end. But that is my general solution. Very good with that. It's general because it's c and it could be anything. Then we have differential equations. It's a different phrase and it's going to sound big and scary, but this is a differential equation. That is a differential equation. It's called a differential equation because they're telling you what is the derivative equal to. That's it. That's all differential equation means. It means what is the derivative? 3x squared plus 2. We could get x cubed plus 2x plus c if we took the antiderivative, but right now it's just a differential equation. Everybody good with that? For example 1, it says find all the functions y. And this always looks weird. Kids get these problems and they look really complicated. But we're trying to figure out what y is equal to. Okay, find all the functions y that satisfy that differential equation. We got dy dx. We want it to just be y. What do I need to do with a problem that says dy dx if I want it to just say y? I got to do the integral, right? What comes before dy dx? Oh, that would be y. And that would set me up for what I want. All right, this first part might not make a whole lot of sense to you, but the first thing we're going to do is multiply both sides by dx. Okay, we're going to get rid of that dx here, and this will make more sense in the future. But right now, we get this problem right here. dy secant squared x plus 2x plus 5, and technically, all of that is times dx. It's fine. But remember the dx, don't let that bother you. That step right there, you probably will never do that step if you are doing this problem on your own, but that's what we technically need to do. If I want to change dy, if I want to change the derivative of y to just y, what do I need to do? Integrate it. Integrate it. Because technically it's like 1 dy. I'm going to take the antiderivative of dy, which is going to get me y. And then I got to take the antiderivative over here. What is the antiderivative? What, when you take the derivative of it, gets you secant squared? Tangent x. And then I'm going to take the antiderivative of 2x. What comes before 2x? X squared. We add 1 to our exponent, divide by our new exponent. We got 5. What's the antiderivative of 5 going to get me? 5x. Oh, and then what else do I need here? Plus c. It's a general solution because we took the antiderivative without any bounds. This right here is my general solution. That is the general solution to that differential equation. Yes, ma'am? No, because when we take the antiderivative dx, it's just saying we're taking the antiderivative with respect to x. So the number 5 becomes 5x. Basically, that's what it's telling me. If we had it on the other side and we took the antiderivative, then it would say 5y. Because on the left side, we're taking the antiderivative with respect to y. Yep. Everybody good to this point? That's a general solution. We've done that before. Nothing new. Today, what we're adding is the phrase slope fields. And that's something that can happen on the free response portion on the AP exam. I think it's the easiest problems on the test. I can teach someone in Algebra 1 how to score 2 points on this every time we do a differential equation. You just got to take your time. A slope field is simply a visual representation of the derivative. What does a derivative tell me? It tells me slope. So it's a visual representation of the slope. That's what we're doing here. Okay, we're finding a visual representation of the slope And we're going to tie that all back into the whitewater rafting we did for Bell. So we could have a differential equation. If we had this guy right here, this is a beautiful differential equation. It's called a differential equation because, again, dy dx, the derivative is equal to something. If I took the antiderivative of that equation, it could be this guy. Okay, boom, that thing plus 3. Or it could be this guy, that guy minus 18. Could be this guy. All of these things are antiderivatives of this. It could just be plus c, or we can figure out what that constant is. All of the functions have the same derivative, but just different by a constant. Everybody agree with me on that? All right. What we're going to do here in example 2a is we're going to sketch multiple solutions to this guy right here. So in other words, right now it's plus c. That c can be any constant. Show me with your arms, what does x squared look like? Boom, it's a parabola. What's the easiest thing c could be? 0. If c was 0, basically we're going to just graph x squared plus 0. All right, well, if we're graphing x squared plus 0, we're going to put a dot right there at 0, 0, and we're going to make a parabola. Okay, remember patterns for parabola? That's 1, 3, 5. So I'm going to go up 1 over 1, up 3, 1, 2, 3, over 1, up 3, over 1, parabola, parabola. There's number 1. What else easily could x, or what could c be equal to? C could be 0, c could also be 1. What would x squared plus 1, what would change about my picture? It'd go up 1. So my picture, instead of being right here, is now going to be right there. It's up 1. And we draw a parabola. Up 1 over 1, up 3 over 1. All right, cool. I kind of go off my page. What else could c be? Negative 1. X squared could be negative, or the c could be negative 1. So the negative 1 would take me down 1. I'd go up 1 over 1, up 3 over 1. That could also be my picture. And we could keep going from there. Go ahead, draw me at least two more parabolas with different c values based on that picture. Go. All right, we could keep drawing forever. In general, your picture should look like that. It's a bunch of parabolas kind of stacked up. Imagine you had a bunch of cups and you stacked them up. They would look very similar to that concept. Everybody agree with me? So that's a graph of the general solutions, which is kind of funky. What we're going to do now is we are going to sketch a slope field. Okay, a slope field for that differential equation. Okay, 2x, because 2x is the derivative of that guy. We're going to just graph the derivative. So to do this, we got to plug in a whole bunch of ordered pairs. Now, the good news is we'll be able to figure it out a little bit. Okay, eventually, we're going to do stuff like this thing down here where they kind of tell you that you're going to graph slopes for all of those points or all of those points. But right here, we just kind of got to graph. So let's pick an easy one. Let's say we were looking at the ordered pair 0, 0. Okay, so we're going to find the derivative at the ordered pair 0, 0. What do you think I'm going to plug in for x? 0. What is 2 times 0? 0. So the derivative at 0, 0 needs to be 0. So what we're going to do is on our graph at the spot 0, 0, we are going to draw, this is the derivative, so I'm going to graph a slope line of 0. It's going to be like a little half-inch line that goes through the point 0, 0 that has a slope of 0. So that little tick mark right there with a slope of 0. And we could keep going. Did it matter on that one what the y value was? It didn't, right? So like if I graphed 0, 1, what would the slope be at 0, 1? 0, right? 2 times 0. The x is what I'm plugging in. My x is 0. So right here the slope would be 0 because the x is 0. Right here the slope would be 0. There the slope would be I don't care what the y is. Basically, anywhere where my x is 0, my slope is going to be 0. Kind of makes sense? Let's pick a different x value. So we all have established on this equation, the y's didn't really matter. What's another x value I could plug in? 1. If I plug in an x value of 1, show me with your fingers, what is my slope going to be? If my x is equal to 1, then my derivative, when I plug it in, is going to be 2 times 1, so my slope needs to be 2. So what I need to do now is everywhere the x is 1, I'm going to make a slope of 2. Now that's kind of hard, but imagine I'm doing slope, so rise over run. I'm going up 2 over 1. So I'm drawing a line that kind of aims for those two dots the best you can. Okay, then right here, same thing. Right there, same thing. Just kind of keep the same slope throughout the best you can. You're not going to be perfect, but you're doing the best you can. All of those have a slope of somewhat 2. Everybody with me to there? What if x was equal to 2? If x is equal to 2, what's my slope need to be? 4. dy over dx would be equal to 4. And so now I'm going to draw a line. What's going to be different about my line? It's steeper. So I'm going to try to, by best of my abilities, draw a line that's a little bit steeper. Now I'm aiming for 4. So I'm like aiming down for that dot. So it's pretty steep, pretty steep, pretty steep. And I'm going to try to repeat the same slope for each one because they're all the same. They're not going to be crazy when they grade it. As long as they're all fairly similar, you'll be all right. What about at -1? What would my slope be? When x is equal to -1, what would my slope be? -2. So I'm going to draw lines down 2 over 1, down 2 over 1. I'm drawing the slope field all the way through there. Again, the y's don't matter. It's just the x's that really matter here on this equation in particular. And then the last one, what if I used x is equal to -2? My slope would be -4. So it's going to be a pretty steep vertical almost line through there. The pink line should look a little steeper than the green. I know that they're going to end up being somewhat the same, but you're going to make them steeper. Do you see how a graph of the general solutions connects to the graph of the slopes? Imagine, so going back to our boat analogy, this is our river over here. Okay, this is the flow of the water. Drop your boat somewhere. Okay, if I dropped my boat right there, what would happen? I'd go down, I'd go flat right there, and then as I go this way, it would go back upward. Oh yeah, it would make a parabola just like we graphed over here. Okay, this is a graph of the differential equation of the slopes. The green line is a more specific version of that. Okay, and we'll get to that more in the future. Everybody good so far? Let's go down to letter A. We're sketching a slope field for the given differential equation. This is on the AP exam. It will be in the free response portion. It'll be worth 2 points. It is the easiest 2 points you can do. All you got to do is graph some slopes. Okay, so looking at this example, all we got to do is go through each ordered pair and plug them in. So for example, let's start at 0, 0, because that's my favorite ordered pair to plug in. If I plugged in 0, 0, what would my slope be? Well, it would be 0 minus 1. -1. dy over dx would be -1 at 0, 0. Cool. So slope of -1. Which thing doesn't matter this time? X doesn't matter, right? So if I plugged in 1, 0, it's still going to be 0 minus 1. So at 1, 0, it's still going to be -1. Right there, it's still going to be -1. All the way there. The x's didn't matter, just the y's because of the equation. Finish that slope field. Make a line on every one of those dots. Go. If you find some patterns, this becomes pretty easy. But anywhere where my y is equal to 2, my slope is 1. Anywhere where my y is equal to 1, my slope was 0. And everywhere here where my y was equal to -1, my slope was -2. That should be your picture. See if your picture matches. They had good questions earlier in terms of like, how would you grade this? It just depends on the problem. But most of the time they will say like, hey, did you get everything on these 2 lines the same or correct? Then that would be 1 point, and then the rest of them would be a point, just depending on the problem. But normally it's 2 points for drawing a slope field. If you screw up 1, sometimes they give you the benefit of the doubt. Don't screw them up, though. It's just as easy as plugging in. Questions here? So far, we've done pretty easy ones. Let's look at part B. On part B here, notice that we don't have to worry about both x and y because it matters each time, okay? Because there's an x and a y in the problem. So what's a good ordered pair to look at? Now let's look at 0, 0. If I look at the ordered pair 0, 0, I get 0 over 0 plus 1. what is my slope going to be if it's 0 over 0 plus 1? 0. 0 over 1. Is 0 over 1 0? Yeah, it's 0. So at 0, 0, I'm going to have a slope of 0. What if it would have been the reverse of that? What if it would have been 1 over 0? That would be undefined. So you got to pay attention to that. Is it undefined? What would the slope of an undefined line look like? Undefined line would be vertical. 0 line, that's horizontal. Okay? One thing that they normally will not make you do is they won't make you graph this point right here at 0, negative 1. Because if I found the derivative at 0, negative 1, my slope would be 0 over negative 1 plus 1. That's 0 over 0. That's indeterminate form. I can't graph that. Okay, so they won't even put a dot there. Just be ready for that. Kind of makes sense what we're doing. Plug in some points. Make your slope field. Go. Don't overthink this as you graph it. Okay. Down here at these two dots, these slopes would be vertical lines. Because if I plugged in like negative 1, negative 1, it would be negative 1 over negative 1 plus 1. Oh, yeah, that would be negative 1 over 0. That's why I'm getting a vertical line down there and down there. Okay. So be careful with it. Normally, they don't even make you graph vertical lines that much, but they could. Okay. Again, if I were to say how would they grade this, you would get 1 point for this and then 1 point for the other ones. All they're looking for on your lines is, do you have the correct slope in terms of like positive or negative slope? And is each line steeper than the one that it should be steeper than? Like, for example, this is 1/2, that's 1/3. So I didn't do it. Mine's not great. They look pretty similar. The best of your ability, try to make it a little bit flatter than the other one. Kind of makes sense what's going on there with slope fields. All right, now let's build a connection between the two. Flip it over to the backside. A differential equation with an initial condition. We have done this before. A differential equation with an initial condition is called an initial value problem. It has a unique solution called the particular solution to the differential equation. So we've done general solutions. General solution is when you have a plus c at the end. A particular solution is when we don't want to have plus c. We are finding the exact antiderivative. Okay, that goes through a very specific point. We did this probably in the beginning of January. Bless you. Find the particular solution to this differential equation. So when you see this phrase, particular solution, oh, they mean y equals. We're just trying to get it to be y equals. Right now it's not y equals. We're going to make it y equals. Particular solution means don't have a plus c at the end either. Okay, for this differential equation, again, differential equation just because it's a derivative is equal to something, whose graph goes through that point. Cool. I want to make this be y. Right now it's dy dx. So what am I going to have to do with something that's dy dx to make it y? The antiderivative. Again, eventually we're going to do this a bunch, so you might not need to write it down now, but eventually we are going to separate that dx to the other side. So technically, I'm multiplying both sides by dx. If you don't write that out for right now, I'm okay with it, but understand that that's going to be pretty important later on. Then once we've separated it, we are going to integrate both sides. What is the antiderivative of dy going to get me? That's just y. Antiderivative of e to the x. The antiderivative of e to the x is e to the x. The antiderivative of negative 6x squared. So I'm adding 1 to my exponent, so now it's x cubed, and my new leading coefficient now is going to be 2, because I'm dividing by 3. Is that it? Plus c. I just found an antiderivative without bounds, so it's plus c. Everybody with me to this point? That is the general solution because it's plus c. I want to find the particular solution, okay, the one that only goes through one value. So to do that, all we need to do is plug in this point that they gave me, 1, 0. So I'm going to take 1, 0, I'm going to plug it in. Well, that's my y, that's my x. So my y is 0. My x is 1. And they'll do this all the time where you get kind of an ugly answer. Who cares? It's fine. Okay. This is just e. That's going to be just 2. If I get c by itself, I'm going to add 2. I'm going to subtract e. That is what c is. C is equal to 2 minus e. The answer to this question then, okay, the answer to this question is this guy right here. y equals e to the x minus 2x cubed. The only difference is instead of plus c, we're going to write in what plus c is. Plus c is plus 2 minus e. That is the particular solution. That is the only equation in all of the land that when I take the derivative of it, it's going to get me this point right here, and this equation goes through the point 1 comma 0. Kind of makes sense on what we did there. Do it again. Solve this initial value problem. So again, fancy way of saying get y by itself. They gave me a differential equation. They gave me a point. So find the antiderivative with a plus c, and then plug in 0, 2 to find out what the actual value is. Go. All right, so I split up my dx. I multiplied both sides by dx. Slade, what do I need to do next? Integrate it. We're going to integrate both sides, so that dy is going to become what? Y equals 1/2 x squared. Good. Minus cosine x. Wonderful. That is his antiderivative. That is his general solution. That's not where I'm going to end. Luke J., what am I going to do next? Yep. Plug in 0 and 2. So I'm plugging in 2 for y and 0 for x. Luke, what is, this is obviously 0. What is cosine at 0 going to get me? That is 1. So it's 0 minus 1 plus c is equal to 2. We're going to add 1 to the other side. So 3 is equal to c. So the answer to my question, what solved the initial value problem? Again, they're going to say this like 50 different ways, but solving the initial value problem is meaning get this guy right here. Y equals 1/2 x squared minus cosine x. But instead of plus c, go ahead and fill in what the c is. The c is plus 3. Questions on example 3. So now we know how to find general solutions. We know how to find particular solutions. We know how to find slope fields. Let's put those two things together, or those three things together. Okay, we're not going to do example 4. Let's look at example 5. Sketch a slope field for dy dx is equal to x over y. So we got x and y, so they both matter here. And then eventually we're going to draw a curve to satisfy that, but we'll do that later. Let's do this first. We're drawing a slope field. Dy dx equals x over y. They gave me these points. Which the order pair we would start with would be 0, 0, but we're not going to plug in 0, 0, because if I plugged in 0, 0, I'd get indeterminate form. Okay, again, they won't even give you that dot if it came to test day. They would just have regular old lines there without a dot. What would be a good point to plug in? 0, 1. If we plugged in the ordered pair 0, 1, I would get 0 over 1. Oh, okay, cool. 0, 1. The slope is 0. Do the slope field. Okay, plot points for all those dots. See what you get. Go. So the two easiest lines would be the axes. On the y-axis, it's all a slope of 0. On the x-axis, they're all undefined slopes. That's why I got vertical lines. This slope is -1. This slope is -1. This slope was +1. This slope was +1. I went from there at this spot at 2, 1. If I plugged in 2, 1, it'd be 2. Okay, my slope is 2. Here my slope would be -2. Here my slope would be 3. Here my slope would be -3. Again, as long as it's steeper than the one next to it, you're pretty good. Just be ready to erase if you're not very good at drawing. Everybody with me to my slope field? Again, that's pretty easy. That's 2 points on the AP exam. That's an easy 2 points, okay, if you know what you're doing. Now what we're going to do is this part. This is the particular solution. This is the general solution. We graphed the differential equation. Now what we're going to do is draw the curve to satisfy the condition f of 2 is equal to 1. What ordered pair is that if they're describing f of 2 is equal to 1? 2, 1, because this is my x, right? Normally says f of x. So it's 2, 1. So go to 2, 1 and put your pencil there. Imagine what's happening here. They gave you the flow of the river. This is what's happening. These are the different ways it's going to go. They are saying drop your boat at 2, 1. And we have to decide what's going to happen. If I went to the right, okay, if I followed this line to the right, it's going to take me up this direction. Everybody agree with me on that? It's just going to take me up. It takes me off my picture, so I don't really care. If I follow this line to the left, what's going to happen as I go to the left here? It's going to start to go straight, right? We're going left, and then we're going to kind of go straight here, because on the axes, the slopes are all 0. So I'm going straight. So I'm going to go straight down. Now what's going to happen as I go straight down? It's going to start curving back to the right and following that line right there. This line that I just drew in highlighter is drawing the curve that satisfies that condition. If I found the differential equation, if I found the particular solution, just like we did up there, where we found the antiderivative and then plugged into one, that is the line that you would end up graphing. Okay, based on the slope field in that initial point. Makes sense on what we're doing there. You don't have to be perfect when you draw the particular solution, but don't overthink it. Imagine it's a boat in the river. Whatever way it's going to take you, that's the way it's going to take you. If you're overthinking and saying, ooh, maybe that pulls me to the left, then you're probably doing it too much. Okay, let's try one more. Example 6. We are sketching that slope field and then drawing that curve. Okay, I will give you some help here just so you don't have to go forever. This diagonal right here would all have a slope of 0. Go from there and try and draw your slope field and then see what you can do with your initial condition. Go. All right, let's look at our picture, see how you did. That is my general slope field. All of these have a slope of 0. All of these have a slope of -1 and -2 and -3 and -4. And then here the slope is 1 and then 2 and then 3 and then 4. Something like that. We are drawing a curve to satisfy the ordered pair f of 0 is equal to 2. Or in other words, that is 0, 2 because it is f of x. Think about it, it's always f of x. That's my x value. So 0, 2. So go on your paper. Go to where you see 0, 2. Drop your boat. 0, 2. There's my boat right there. We now need to decide what that's going to look like. Think about what's going to happen as I go to the right and what's going to happen going to the left. Show me with your arms. What does your picture look like? Yeah, it's a little awkward, but that's all right. All right, let's see if we agree. As I go to the right, what's going to happen as I go to the right? Which way am I going? Up and to the right. Oh, yep, it's going to make it steeper and steeper. Boom, that's the right side. As I go left, or as I go this way, what's going to happen as I go left? It's going to flatten out for a minute, and then what's going to happen as I keep going left? It's going to go back up. That right there is my picture. Again, don't overthink it. Just follow the flow of your graph. That the whole slope field is all about drawing the river. We drew the river, drop your boat, and see where it floats. Make sense? That